Okay, hello everybody. I see one. William, can you hear me? Thank you. Okay, so let's start. This is just a reminder, the first slide of where you can find all the dates of the evaluation events, including the next text, which is at the end of your reading week on 1st of November at noon. So we covered all of that in lecture 1, so you can find it. You go to lectures, lecture 1, it says course outline and logistics. So when you click on these slides, you can find all the course logistics there. Okay, that's number 1. Number 2, I made a few small corrections on assignment number 4, both in the PDF file and in the starter code. So please re-download it. And I listed them in my announcement just for the benefit of those who already started. One thing I would like to point that now that we've seen lists and loops, as I mentioned before, you can solve every problem that has ever been solved. But that's different from knowing how to solve problem, develops problem solving skill. And you should really aim for that, especially if you are new, if any of this is challenging. To do this, you have to solve as many problems as possible. I know that these assignments can be challenging, and it's on a purpose because you have to code, and you have to code a lot. And yet it's still only 6 assignments. Nobody learned how to be a good programmer by just doing 6 assignments. So you have to complement this with more work, especially if this is new for you. And I couldn't encourage you more strongly to, now that you've seen this is where the critical thing is. It's not objects, it's not recursion, it's not any of these things. It's actually solving problems with loops and usually iterating over some collection, either a list or a string. Okay, this is where you develop your problem solving skill. So for that reason, I suggest to everybody super strongly that you solve all the problems, especially chapter number 5. This is where you have loops and where you have lists. So there's about 40 programming questions. They start from easier to more difficult, like those things that you usually have in part 1. Write a function, does blah. So that's how you develop your skills. Of course, in fact, what I recommend is that you do everything at the end of chapter 3, 4, and 5. So in chapter 3, you have if statements, function design, and variables. So you do problems from there. Chapter 4 is strings, I believe. Yes, so it's strings, more about print method. You can skip the files. We didn't do the files. So if you see the problem involves the file, you just skip it. But again, critical one is do everything in chapter 5. Okay, all the problems that you see in chapter 5. Okay. So that's my recommendation, because I very often get questions from the students. I don't know how to start. How do I develop this? How do I learn this? This is not, you learn it, think of it as math, but hopefully more fun because you code it, you get instant feedback. You develop the skill by solving lots of problems. And again, this is one of the reasons I recommended this book. Go to the end of chapter 5 and do all the problems there. When you get stuck, go to the TA office hours and do it. Which reminds me, this week, of course, you have labs. Your labs are held by teaching assistants, so they're not affected by the strike. Strike is by staff. So you're going to have your labs. Apparently, when I posted lab number 6, the label said 5. So you have a lab day, but there was a wrong label on it. So labs are there. So this week you have a lab. Next week is reading week. There's no lectures. There's no labs, but office hours take place as normal, right? So you're going to have access to TAs for help, whether you're working on your assignment or you're preparing for the test. So you do take advantage of that. All right, that's all I have about course logistics, and I'm ready to teach unless somebody has questions. Any questions?
I have a question.
Oh.
Yes, Celine. Celine, then William. Go ahead, Celine.
Hi, Professor. Can you hear me?
Yes, I can hear you.
I had a question concerning the submission of the assignment. For the small.txt and smallish.txt, do we have to submit it? Because I noticed
No,
when
no,
we
no,
run.
you just submit the .py file. Sorry, yes.
Okay, because I
You-
ran it and it was in a different file, and it said no such. The directory doesn't exist.
You
Something
have
like
to
that.
have to put in assignment number 4 all the files that I provided you. You have to put them in the same directory, and otherwise Python won't be able to find the path. Or you have to modify the line about opening the file, but I don't suggest you do that. You just put you put your program and the text files I provided, you put them in the same directory and same folder, and then it's going to work. But what you have to
Okay.
submit is basically just .py file, your solution,
Okay, so we don't submit the TXT files.
not the one that
Okay, thank you very much.
No problem. Next one, William.
Will you go over what's going to be on the test after the reading week this class?
Basically, yeah, I wasn't planning to actually. I wasn't even, I forgot that the test is taking place. But everything that we have seen up to today. Today, we're going to, for the first time, talk about efficiency of algorithms, so-called big O notation. You won't have big O notation, but yes, for the code, we're going to solve some problems on the list. And I'm going to ask you, is this solution better than this? And we're going to understand what that means. So big O that you're going to see today won't be, but anything else, yes. So it's going to be a format that you have seen in test number 1. It's going to be solving some problems on the list and more strings. And for example, anything that you had in your assignment number 4, you should do assignment number 4 because it involves list, and you may have some functions like what you're developing in assignment number 4 you may have on your test. So here's what we've done already, except it wasn't a function. We just did it in a main. How you find a maximum in a list. So you have a list n, and I want to return a maximum. We said that in a list, you just assume you take a first element, and that's currently your maximum. Then you go through the elements of the list one by one. Each time you take next element, you compare it to your current max. And if my current element I'm looking at is bigger than the current max, I update the current max to the new maximum. And I continue. By the time I get to the end of the list, we have what is stored in current max is the maximum. Okay, that's one solution that you can do this problem. So let's see, how many operations does this do? Okay, so if I ask you, how many operations does this type of solution do? Hopefully, you will say, well, it depends, right? If the list has 100 elements and if the list has 1 billion elements, in this type of solution where you look at every element of the list once, you read every element of the list once, you don't do the same number of operations, right? So it's going to depend on the size of the list. Typically, that is your input, right? It's that your solution will typically depend on the size of the input, okay? So when you, from now on until the end of the semester, and actually throughout your computer science studies, typically when you hear variable n, it refers to the size of the input. Okay, so in this case, input is a list. So you can assume whenever I'm talking about n, that means in this case, length of the list. We have a list as an input, and size of that list is the number of elements in the list. So when I'm talking about n, this is just the size of the list. And I will usually want to figure out how many operations does my solution do on a list of size n, okay? So let's look at our solution. By the way, this solution, as we already seen, even this question only makes sense if a list has at least one element. What does it even mean if you have an empty list to return a maximum? It's not even well defined. So we are assuming that the list is non-empty. And first of all, on an empty list, this will already would crash. So we're assuming in a precondition that the list is not empty, that it has one element. We take the first element, that's our current max, and then we continue and update it as needed. Okay, so let's analyze how good is this solution, or rather, let's even forget about good or not. Let's figure out what is it that we are counting? What is it that we are doing here? Okay, how many operations does this solution do? So what you want to count is roughly the number of operations your solution does, because that's what costs you. Okay, so let's look at the first line of this program, of our solution. What we're doing here is on the right-hand side, we are accessing the first element of the list. Python and all the other programming languages, a good thing about list is that if you give me an index, I can basically what is considered, that's one operation. You can or at least constant number of operations, 1 or 2 or 3 to access, given an index, let's say, give me 100 element, you can say that's one operation. I just jump to the 100 position, and that's one operation. So accessing his element in the list is one operation. And then assigning that to a variable, that's also just one operation. So basically, this for us, accessing a value and assigning it, you can say that's one operation. It could be 2 or 3, but that's a small constant. We don't care. We're counting that in 1. This is like one operation. Okay. We have another one here that also looks like one operation. Okay, we are assigning some value to a variable. Okay, sometimes, very often, so if you're adding the 2 numbers, that's one operation. So if you're assigning a value to a variable, that's one operation. If you're comparing 2 elements, that's one operation. So roughly, these are the things that you can count as one operation. Sometimes that is equivalent to saying 1 line of code is one operation. In this case, it's kind of like, it looks like, okay, 1 line of code is one operation, but we will see you have to be very careful with that statement. It is not always true, okay? Only if that line is doing something simple like this, assigning something to a variable, adding 2 numbers, multiplying 2 numbers, comparing 2 values, and so on. Okay. So let's see here, we come to this line of the code. We have a for loop. First time I encounter this loop, what this does, it takes the first element of the list and assigns it to variable item. So it does L of 0, item is equal L of 0. That's literally what it does. So that's again one operation. So first time I execute this line, first time I execute it, or each time I execute it, I do one operation. But how many times do I execute that line? So you can unmute yourself. Does somebody know how many times do I execute this line?
L time.
How many times?
L time, like, depends on the number of elements.
Not L. L is the name of the list. So N,
Length.
number
N
of
time.
elements in the list. N, right?
Okay.
So exactly. But you're right. I know that you meant correctly. I just want to make sure we're saying the correct things. Okay, so we execute this line N times. So times N, and each time we execute, we do N operations. So total number of operations this line cost us is N. So far we have 1 plus N operations. Okay, how many times, so this, look at this line, how much this cost us? If we executed 1 time, we're just comparing 2 elements. Is item bigger than, that's 1 operation. But how many, so we have 1 time, when we execute this, that's 1 operation. But how many times do we execute this line? Anybody?
N times.
Also N times.
N times.
N times, exactly. Every time we enter the loop, and we enter the loop N times, we execute this N times. Okay, we come to this line. If I execute this line once, this is just assigning a value to a variable, that costs me 1. Okay, that's 1 operation. But how many times do I execute this line?
Once.
Why once?
Depends on how many times there is the max. We find the max.
Exactly. It depends how many times do we get a true here. But so every time we get a true here, we enter and execute that line. So we don't know how many times you're going to get true. But what I really want to say, I want to be able to say something like this. I guarantee that my solution does at most 100 times N operations. Okay, at most. I want to guarantee in the worst case how many operations I can always guarantee no matter what happens. So what we can say, why I don't know exactly how many times this line can be executed, it can be 0, right? Because this can always be false. I know that it's at most 1 times N. Okay, so it's at most 1 times N. And then I have this current max returning 1 value, that's 1 operation. So we add up all of these things and we end up with, that tells us how many operations we do, this solution does on a list of size N. Okay, so what do we have? We have 1 plus N plus N plus N, that's N plus 1. So that is, so we do, and here we have less than equal. So the number of operations at most 3N plus 2. Okay. So our solution does at most 3N plus 2 operation. So suppose somebody comes along and they have their own maximum function and they say, okay, my solution, I guarantee that my solution does at most 4n minus 1,000 operations. Which one is better? Which one is better? Well, actually, sorry. This one should be clear because this one is always smaller. What I want to say is this, which one is better, right? If I had 3n minus 1,000, it's always less than 3n plus 2. So this one should be better, right? Anyways, but I wanted to say this. Okay, in this case, it really depends on the n, right? For some, if n is 1,000, this one is going to do 3,000 operations. Oh, this is a bad example. Let's say, in fact, this one actually doesn't make sense because when n is 100, this one seems to be do a negative number operation, but I just invented it. But in either case, let's say n is 2,000. Here we would get about 7,000 operation, and here we would get, what did I say, 2,000, 6,002. In this case, this one looks better. When n is 1,000, this one would do 3,000 operation. This one would do 3,002 in this case. So this one looks better and stuff like this. But this is too fine of analysis. What really matters is how fast n grows, because n is what changes. These constants here don't play such a big role. Okay, what really matters is this. And I'm going to demonstrate this. We're going to do experiments at the end of this class, and you're going to see a dramatic difference about what's going on with n. So I really don't care. I want to know what's going on with n. How fast of a function did I get in terms of n? Is it n? Is it n squared? Is it 10 to the n? How many operations am I doing? Okay, so this is what you're going to be doing in computer science, the way you analyze this. You're going to say, I don't care about constants. And you're going to indicate that you remove the constants by using a big O notation. This is so-called big O notation. So you're going to look at this solution and say, I'm going to remove all the constants. Okay. And here, if you remove constants, is really absolute constant. Here, absolute constant is 3, something that doesn't depend on n. 3 and 2 don't depend on n, except that you will not be removing them in the exponent. Okay. But for now, in these two solutions, I'm going to remove a 3, I'm going to remove a 2, I end up with n. So I'm saying my function does big O of n operations, meaning it does roughly linear number of operations. There may be some constants there, but I'm ignoring them. Let's do this with the second solution. I remove a 4, I remove 1,000, I end up with also big O of n. So both solutions do roughly linear. What is linear? Linear function in n to the 1. N to the 1 rather than n squared, for example, right? N is n to the 1, is the same thing. That's why it's linear. Linear function is function where dependence on n is n to the 1. In both cases, these are linear solutions, okay? And so they are roughly the same. Okay, so big O notation is just saying you are doing roughly n operations. I'm ignoring some constants there. So in that sense, the solution that does this many operation, they are roughly the same, okay? All right, so let's look at different type of solutions for finding a maximum. Okay, so you could do something like this. Does anybody have an idea how to find a different idea how find the maximum is by, oh, here's a question. Can we do better? So this is what computer science is about. Not only figuring out how good, what is the number of operations that my solution does. And by the way, official name for that in computer science is what is the running time of your algorithm. And time doesn't mean time in that. When you hear running time, it doesn't really mean time in seconds. It means number of operations. So the running time of this solution is O of n. It's linear in the size of the input, okay? So can we do better? Can we find maximum faster than O of n? Okay, is it possible that we can design, so we are guaranteeing, this says, I guarantee that no matter what type of list you give me, the maximum number of operations I'm going to do is going to be roughly linear. It's going to depend linearly on the size of the input. Okay, so the question is, can you do better? Okay, is it possible, for example, that you have a solution that guarantees n to the 1/2 operations? That's square root of n. Square root of n, n to the square root of n, it's much slower growing function than n. Okay, so for example, when you have a list of million, this is going to do roughly million operation times some constants, and this one, square root of million, is what, 1,000, right? So this one is going to do the roughly 1,000 times some constant operations. So I'm just giving you an example what would be faster algorithm. So is it possible to do better than linear?
Wouldn't it not be impossible? Otherwise, you cannot check. You cannot verify every
Exactly.
item in the list.
Very, very good. Okay, exactly. Let's try to convince ourselves, because this is one of the. So there are two things you're going to study in computer science. One is you design an algorithm and you want to say, I guarantee that no matter what you give me, I'm going to do this many operations at most, no matter what you give me. That's upper bound. I'm saying at most, upper bound on number of operations. The other thing where you're designing the lower bound, when you're saying you cannot do better than this, these are very hard to prove. Both can be quite demanding to prove, but lower bounds can often are much harder to prove, showing that it's impossible to solve, no matter who solves it, that something is impossible to solve faster than blah. Okay, but this is one example where it actually should be easy to figure out. If you don't know anything about the data, about what's inside of your list, okay, if you don't know anything about what's inside of your list, in which way your list is given, then, and imagine that if you say, I can guarantee less than n operations, but if you guarantee less than n operations, that means that there is at least one element that you didn't read, that you didn't look at. Okay, because if you do less than n operations and you have n elements of the list, just reading each element of the list is going to cost you n. You have n elements, access first element, access second element, access third. If I'm going to access every single element, that's already n operations. It's really n operations on a computer. If I'm going to see read x, read L of 0, L of 1, L of 2. So that means if you're going to do less than linear number operation, not to mention asymptotically less like this, like square root of n, that means that there is a number that you didn't look at. How do you know that number is not a maximum? You don't. Okay, so in fact, linear is best possible here. So we designed, this is called optimal. When you find a solution that the number of operation is actually best possible that you can guarantee. So in the worst case, that you guarantee that you're always going to do at most n operations, and that there is no solution that can guarantee better than linear number, then you have an optimal algorithm. So this is an optimal algorithm. Tony, you have a question.
Yeah. Hi. So you just said like you need at most n, right? But since we already assigned the current max to L0, right? So why do we still need to read the first one? So we only need n minus 1, right?
Yes, but you are talking here -1 plus 100. First of all, it costs you 1 to read this, and then you read the rest of them. That's 1 plus n minus 1. That's already n. Okay. And again, remember, we are ignoring the constant. So n minus 1 is n. Okay. I'm talking about, can you, when I say, can you do asymptotically better? Can you do function better than linear? Okay, we are ignoring the constants. It's very important to ignore the constants, that otherwise this analysis is impossible. And you will see in the experiments that run that that is all that matters. Okay, all right. So normally, by the way, here's another solution, for example, that sometimes students suggest. In fact, it happened in previous class. Okay, so let's look at this solution. Maximum version 2. All right, I do this, L sort. I sort the list. When I sort the list, where is the maximum? It's at the end, right? So all I have to do is return the last element. Okay. This looks much nicer than this one, but is it better? Okay. So, all right, let's first start with this. This is just accessing the last element of the list. As I said, accessing individual element of the list, you can do, that's one operation. So you're just returning one value, that's one operation. Okay, but this is a loaded one. Remember when I said, when you see one line of code, if you executed one, sometimes you can assume that's one operation. When can you assume it's one operation? What did I say? When you assign, you take a value, assign it to a variable. You compare two numbers, you add two numbers, you multiply two numbers. You can assume these are one operation, but one line of code is not equivalent to one operation, especially if you have a function call. So look, what is this? You are calling somebody else's program, literally. You're calling sorting function of Python, and you're sending it a list L that has size n. What do you know how many operations does their solution do? You have to know that to be able to say, is this better or worse? Because this looks like, oh, if it's really one, then this is, you know, one operation. We have two operations. Wishful thinking. You're calling somebody else, you're calling a whole program of somebody else. So whenever you're calling a function, you have to know how many operations does this function do. So Python sort function, you're sending it to the list of size n. How many operations does sorting take? This one line and one call, I can tell you it's not one. It's not even this. Okay. By the way, this just, I want to at this point just mention that a game of, while it's fun, of writing solutions that have as few lines as possible, it could be fun, but it's meaningless. It has nothing to do with efficiency of algorithms. Meaningless in terms of efficiency of algorithm. It's meaningful, it could be meaningful in terms of readability. You shouldn't write spaghetti code, and you know, you should try to write readable thing, but making as few lines as possible can also make your code unreadable. So all I want to say is that the number of lines of code has nothing to do with efficiency. Okay, what you want to do optimize is the number of operations that your solution do. Okay, so this one, you have to figure out how many operations does this Python function do. In fact, you can Google this. I told you that the keyword is running time. You can type Python functions running time, okay? And sorting, you can figure, sorting is roughly, if you do the best sorting algorithms, they do this many operations. Okay, so it's n times log n. Okay, that is more than this n. This is linear functions. This is more than linear. Okay, this is n times 1, right? So you're the difference here is log n versus 1. That's a big difference. Log n is a super slow growing function, but it's still growing. It still depends on n. 1 doesn't depend on n. Log n is typically what you're going to strive for because it's super slow going. Remember, log of 1,000,000 is 20. Okay, but still it's a growing function with n. So this is more. So this solution, this line costs you n log n, this line costs you 1. So what you get is basically n times log n plus 1. I said you can ignore the constants. So this solution is an n log n solution. So it's worse than this. And this one is linear. Okay, one is linear, one is n times log n. So this one does more operation. This is an outlier in a sense that very often, sorting makes solutions faster because otherwise your solution is quadratic or something worse. And it makes solutions simpler. You can see here, this is super simple, right? Once somebody sorts the data for you, if you want the maximum one, you just return the last one. In fact, typically, if you're holding lots of data, you should keep it sorted, all right? But that's a story for a different, you're gonna be studying this in data structures and algorithms. How you keep the data sorted under the condition that you can add something to it and remove something to it, and you still want to keep it sorted, and you don't want to redo all the sorting things, but that's on the side. Okay, so we had two solutions here, and the first one is actually better and optimal. Okay, so we have a linear solution for finding a maximum. By the way, another solution that you may have designed here, and students ask me, like, can I use Python's max? Because they don't want to write their own max, which I understand, right? I would probably ask the same thing. Right, here it is. Just call Python's max function. Okay, so how many operations is this? It's definitely not one, because you have one line. Before you can return a value, returning a value is one, but what value are you returning here? You have a function call again. So this, you have to figure out how much does this cost me, calling max on L, where L is a list of size n. And I can tell you that Python 2, this is going to cost you O of n. So this call here does n operation. And then let's say this returning the value is +1. So it's again a linear thing. Okay, so if you did Python, if you called Python's n, you would get a linear solution. So basically it does this. Okay, this is universal solution for finding maximum. Okay, let's solve something else. And I made this second example a little bit artificial, just so it has something similar to loosely related to what you do in your assignment, really loosely related, don't get, okay, so let's say we have, I call this positional min. Let's say we're given two lists, X and Y, and imagine that you want to represent a set of points in the plane. Okay, so typically you are given a point by giving the S coordinate and Y coordinate. So let's say I want to represent 3 points or 4 points in the plane. I want to know X coordinate of 0.1, 0.2, 0.3, 0.4, Y coordinate of 0.1, 0.2, 0.3, 0.4. I want to store them. There are various ways to do it, but one of the common ways to do is simply to have two lists. Okay, they're called parallel lists because their data is related. So for example, I would say that my first list is 1, 2.5, 100, minus 8. Okay, so the X coordinates of these points are these. Okay, and Y coordinates of the points, I don't know, 2, 0, I don't know, 80 and 20. Okay, so here the data in list X and list Y are related because the information in position 0 of both lists represents X and Y coordinate of 0.0, first point. Okay, so the first point has X coordinate 1 and Y coordinate 2. The second point has X coordinate 2.5 and Y coordinate 0. More generally, point ith point, if you have n points, ith point, if you want to know X and Y coordinates of ith point, you would go to position I and say in list X, so X of I gives you X coordinate of point I, and Y of I gives you Y coordinate of point I. Okay, so in some sense, the data in X and Y are related. What does this have to do with your assignment? I just wanted to introduce this notion because you're going to see it parallel list. It just means you have a two list with the same number of elements, but the data in each position, position I, position, are somehow related. So in one of your questions, you are given a list of words. I forgot exactly what. So you're given a list of words. That's your input, word 1, word 2, word 2, 3, and so on. Okay, and what you have to output is a list that you take in the first position. You have here word summer. Then in your return list, in the first position, you have to give number of anagrams of that word. Let's say summer has 2 anagrams. Then in the second position, or index 1, you have a word today. Then in return list, in that same position, you're going to have number of anagrams of that second word. Let's say there's 3 anagrams for this, and let's say there's 0 for this. Okay, so somehow these two lists are related in terms of data they carry, they're parallel. What you have in index I here is a word, and in index I here is how many anagrams that word has. Okay, All right, so what do we code here? I invented, so forget about assignment now, we go back here. What I want to call here, I'm going to say that list L, so the coordinates L, are smaller than coordinates in Y if for each position, for each point, I have, for each single point, I have that point, that X coordinate is smaller than a Y coordinate. It has to be true for all the points, okay? For each point, I need that the X coordinate is smaller than the Y coordinate. So let's see if it's true here. First point, X coordinate is smaller than Y coordinate, excellent. Already we have here that it's not, so I return false. I can stop and return false. Let me modify this. If I had here something like that, and here 22.5, okay, let's look at it now. I want, what do I want in order to return true? That for each point, X coordinate is smaller than Y coordinate. I have here, one is smaller than one is smaller than 2, so far so good. -2 is smaller than 0, so far so good. 22 is smaller than 80, so far so good. -8 is smaller than 20, great, and we are at the end. Indeed, all the points have X coordinate smaller than Y coordinate. In that case, I want to return true. Okay, so I hope you understand the problem. If for all the points X coordinates are smaller than Y, we return true, otherwise we return false. All right, so let's code this. So this was just a comment, so we remember what to do. So we have two same lists with the same number of elements. We have to go through all the elements of this list because for each point I have to look at their XY coordinate. So therefore I need a loop. What does the solution require? I need to look in position I of the list X and Y. That is the data for point I. So I better loop over the positions in the list, right? So I do for I in range. What's the length of the list? They have the same length. So I might as well just say length of X. What did we say? What do I want? I want that the X coordinate of point I is smaller or equal, let's say smaller or equal is what I want, an X coordinate than Y coordinate of point I. Okay, so if that's true, I just take the next pair, I continue. Okay, so I test that. Okay, so what do I do now if it's true? There's really nothing to do. I just read the next pair. Only if it's not true, I have something to do. If it's not true, I found an outlier. I found what I don't want, so I immediately can stop and return false. Okay, but this part of code seems kind of, why do this? Why do I simply not test? You should also, what I want to show with this is that you should also test what, you should also think, what should I be asking? Because if xi is less than equal yi, I get what I want, but I don't know yet what the answer is. I just continue. You might as well ask something that if it's true, you immediately know the answer. Okay, so if I ask here, I can ask, are you an outlier? Is it true that X and I is bigger than Y or Y, which is what I don't want, right? If that's true, I immediately can stop. I just return false. Okay, both are correct, but this kind of makes more sense to ask. So I'm just saying, even that you should think about. What are you testing? Okay, so I'm saying if X and I is bigger than Y or Y, I should just return false, because I already know the answer. Otherwise, there's nothing to do. We take the next element, right? So if I ever make it out of this loop, I know that we compared the X and Y coordinate of each point. So I might as well then return true, because I've compared them all. I didn't find anything that is against my rule that I wanted, and now I can return true. Okay, so that's the solution. It's a correct solution, and so on. At this point, I would like to, it used to be that in the early years of this course, the students used to write code, like the way you had test one, the exams were, of course, you couldn't have a computer. And the students would write code on a paper. And it's a bit nightmarish to write code on the paper. It's very difficult to write correct code on the paper. It's really difficult. It's difficult for the students. And then once students are done, it is difficult for us to grade it. It was a bit nightmarish, right? So, but you know, that's the system. You controlled, you're in the big gym, 1,000 students. You don't have a computer. Of course, you don't have access to computer for all the obvious reasons. And you're writing the code because this is a programming course. Okay, so I want to show you type of a mistake that I was getting all the time. All right, that's number one point thing that I want to point out. But at some point, this was so nightmarish for everybody. We moved to the multiple choice questions. That was what we did last 4 or 5 years for this course. Okay, but in fact, I know that this COVID is nightmare for everybody, okay, from every aspect of life. But if there's one positive that you guys can think of, and I think this is really bad for everybody to be online, this is no fun, right? You're not with your friends, you don't have motivation, you don't have peer support. I mean, this is bad in every possible way. But one positive thing in this is that you actually can code for your exams, okay? You have a computer and you're coding for your exam. You're literally the first generation that is doing this, simply because there is no other option, right? Normally, you have 1,000 students, they go to a gym, there's no way that this can be logistically implemented, that you are coding, that you're actually coding on a computer for this. So this is a plus. But here's what I learned, I'm going back to my story. So here's what I learned about type of mistakes the students do that demonstrate you have to think, you can't do pattern matching in this. So I would see huge, I would say 30% of the students. So type of question, here's a mistake, for example, that I would see. I'm showing you a mistake because you learn from mistakes too. Okay, so, you know, here's a very common pattern. Okay, before we start checking if I have what I want, I might as well assume that the result is true, that everything is in order. Then I start checking, is indeed everything in order? And if it's not, once I find that something is not okay, I set this result to false, okay? All right, so far so good. So this says, all right, so if I find, so I check pairs, everything is fine, I check the pairs. But if I find a pair where the x coordinate is bigger than y coordinate, here's my outlier. So if this is true, I do a result is false. If this is where you stop, that would be great, but no, because if you don't think, if you just do patterns in students' head, it's like, oh, when I see if, it's usually if something do blah, otherwise do blah. Okay, so you would do this, result is equal true. Okay, I would see this everywhere. And then return result. In fact, in one of your labs, I made a question like that, which says, is this solution true? Based on these mistakes that I saw, is this solution true? If it's not true, give me an example where this fails. So this solution is dramatically wrong. I don't know how else to put it, okay? So what is it that you're doing? Notice this, every time you compare these two, you're actually changing the answer. So you completely, no matter what happens here, you are setting this value. So everything that happened before is forgotten. So if somebody asks me, what does this program do? I can tell you all it does is compare last two elements of list X and list Y, because that's what is stored in result. If I ask you, when would this give a wrong example? Here's when it would give wrong example. I have something like this. So when we are doing our third point, when I is 2, you enter here and you say X of 2, is it bigger than Y of 2? And indeed it is. So this is true. So I should actually return false. I should set the result to false and never put it back. Once you find an outlier, you have to think what you should do, not just pattern match. Oh, this is how you do this, and you just memorize it and put something there. All right, so result is false. Then I take the elements that come after, which is the last element in the list. I come in and I say, X of 3, is it bigger than y of 3. No, it's not. -8 is not bigger than 20. So this is false. I come here and I put it to true. And then you return true. So you completely overwritten what you put before. So again, what this does is really just compares the last two elements of the list. Okay, if you did something like that, though, this is completely true. Okay, so that was just to demonstrate it, that this is problem solving and not pattern matching and memorization. And the way to learn this and develop this, this is the skill that anybody can develop, but you have to solve problems, okay? Just the speed can be different, but anybody can develop problem solving skills. All right, so let's now analyze the running time. Like I already mentioned, we might as well do this one. This is one operation. This again, this line, this thing, what does this do? Range produces first 0 and 0 is assigned to 1. So first time we execute this line, we are literally doing this. So one time we execute it, we do I is equal to 1, that costs you 1. Next time I execute this line, you literally do I is equal to 1, that's one operation. Next time I is equal to 2, that's one operation. So each time I execute this line, again, I'm doing one operation. How many times do I do this line is the number of elements in X, which in my case, as I told you, size of the list, I will always indicate by N. So this line is execute, costs you N, 1 times N. This line here is also executed N times. And each time you execute it, you're just comparing two numbers. So that's one operation. So number of operations you do here is 1 time N. This line here is executed, we don't know how many times executed, but it's at most N. And again, we are just assigning a value to a variable. So that's one operation that may have been executed N times. And here we are returning a result that's executed 1 time. So the running time of this algorithm, well, it turns out again that's 3N plus 2. This is just accident because I was looking for short examples. Again, I told you, you remove the constants, so you remove 3 and 2, and you get big O of N. Okay, so this is also a linear solution. Okay, now something different, okay, that may or may not be linear. So far we've seen two solutions that are linear. So here's a problem, one of the most common problem in computer science is finding duplicates. It appears everywhere, okay? So what is the problem? So you're given a list. You're given a list, I'm gonna call it L just for readability purposes. So let's say a list of numbers, even list of it, doesn't really matter, any form. And then here's what I want. I say that the list has a duplicates if there is an element in the list that appears at least twice. Okay, so let's say, let's understand it on example. So list like this, 102 minus 200.5. Although I was saying ins, it doesn't really matter. Does this list have duplicates? Is there an element, is there a number that appears at least twice? The answer is no. Do we have duplicates? No, we return false, okay? A list like this, for example, I do 100 and maybe even 100 here. Does this list have duplicates? The answer is true. There is an element, in particular 100, that appears at least 2 times. This is, as I mentioned, this is a super common problem that appears everywhere. And typically you want to remove duplicates or you want to merge them. And I'm sure you encounter it everywhere. In your address book, for example, Google often offers me for my address book saying, are these two people the same? You want to merge their contact information. For your pictures, you definitely don't want to have duplicates. Pictures take space on your computer. You want to remove duplicates. In fact, this is a huge problem that appears everywhere. For example, you would think the banks wouldn't have an issue knowing does this bank account and this bank account, do they belong to the same person? They want to know that. Is this true that these two banks account belong to the same person? And you would think that's easy to figure out, right? You know, you have a social insurance number of this person and social insurance number of this person who opened this account. But actually, no, you don't necessarily give identifying information, such a strongly identifying information, such as social insurance number when you're opening your account. It could be that the person in one city opened an account and gave their middle name, and in the other one they didn't. They don't know exactly. It's a huge. So I have a friend, she's an executive in a bank. This is a huge data mining problem, or actually data learning problem, figuring out which accounts belong to same individuals. Okay, but this one is more complicated than just this duplicates problem. Okay, all to say that this appears everywhere, solving duplicates problem. So let's go back to what we want to solve. We really are just working with numbers, and we want to determine, does the list have an element, at least one element that appears at least twice. So this is the best way to visualize these type of problems. How would you solve it? So usually in the class, I tell students to imagine that I lay down, let's say 1,000 cards, 10,000 cards, even better, cards, like a playing cards. But one side has just an image, same image, like the cards, but the information side has only the numbers. So you only see the picture size. You don't know what's on the digit side. And they are lined up 10,000 cards, and I'm paying you to do the following. I'm paying you to go through these cards and tell me, are they duplicates? Okay, so there are numbers on the other side of the card, on the hidden side of the card. Okay, and the faster you do it, the less operations you do, the more money you get. All right, so what you're allowed to do, so I usually ask you, what's your procedure? This is not, if you say something like you just open all the cards and eyeball them, well, I'm going to say I'm going to give you 10 million cards. You can't eyeball. It has to be a systematic operation that guarantees to me, I want a procedure that guarantees that you're not going to make a mistake, and yet that you're going to do as few operations as possible. Because you know how much I'm going to pay you is depend on time, inversely depend on the time. The less time you spend, the more money I'm going to give you. Okay. All right. So I ask the students how you do this. How do you do this?
If there's more cards than 52, then there's than 54, then there's duplicate because of card game.
No. I changed the problem. They're not playing cards.
Oh, sorry.
What's on the card? No problem. What's on the cards are integers. So you have a picture on one side, on the other side, integers that you don't know what they are. Really like in our example. But you are right. If it was real playing cards, I can do 52. If there's more than 52, I can immediately say, yeah. Any other procedures? Can somebody says an actual procedure? Okay, let me give you a first procedure. I'm sure you're going to come up with some other. So here, actually, I didn't tell you the rules. Here are the rules. The rules are, I allow you to open 2 cards because you actually have to compare. To figure out the duplicates, to prove to me that you have duplicates, you can show me, here are 2 cards, they are the same. Okay, so I allow you to open 2 cards at a time. You compare them. If they're same, great. You're lucky, you get your money and run. If they're not the same, you pick a new pair. Okay, and how many pairs you open, that's your number of operations. How many pairs you compare. So here's one procedure. I take a first card. I open the second, and I compare them. If they're the same, great, I can stop. If they're not the same, I close the first one, a second card. Sorry, I'm still holding the first card. I close the second card. I open the third card, and I now compare first and third. If they're the same, great. If they're not, I continue. Close the third, open the fourth, and compare first and fourth. So so what is my procedure? I compare first and second, then first and third, then first and fourth, first and fifth, first and last. Am I done? Can I conclude that is my solution? Can I conclude yes or no after going through one phase of this?
No.
No. It could be that 100 and 2,000 are the same. I am done with one. With the first card. If I didn't find anything same with the first card, I'm done with the first card. That's all I conclude. So I put the first back, I take the second and repeat with the second. I compare second to everybody one by one. Then I take a third, compare it to everybody one by one. Then I take a fourth card, compare it to everybody. Finally, I take the last card and compare it to everybody. Okay? If after I do all of that, I don't find duplicates, I can safely say, no, there are no duplicates, return false. Otherwise, at some point, I will bump into two cards that are the same. Okay? So let's code first this solution. Okay, then I may ask you, can you do better and stuff like this? Okay, so let's code this. So what does our solution say? It says take first card, then take second card compared to everybody, take third card compared to everybody. So let's code this part where I say take first card, take second card, take third card. Well, I need a loop for that. And in particular, my solution is speaking about position. So I better use I better use positions. Okay, Juan, you are unmuted. Can you mute yourself, please? Just for the noise. I think it's the, okay. So, first time I enter this loop, L of I is 0. So I'm holding the first card. Okay, I'm holding the first card. So now I'm holding. First time I enter the loop, we are looking at L of 0. Let's just comment for myself. So what do I have to do now? I have to look at all the cards. That means how I'm going to look at the cards one by one. That means I need another loop. Okay, so I need a loop to compare everybody to L of 0. Okay, so I need another loop. I write another loop for J in range. So I use a different variable, right? It's a loop that goes again through the list. L, len of L. All right, that's the loop. By the way, often I get these questions. Can we do nested loops? Can we use nested loops? These questions doesn't make much sense. You use a loop when you need the loop to solve a problem. Okay, so here, I enter a loop. What is now inside of the loop? I ask myself, what's the problem that I have to solve now inside of this loop? The problem I need to solve is that I'm holding card L of I. So in this, when you just enter first time, it's L of 0. I'm holding L of 0. Now this card, L of I have to compare one by one to every element in the list. How do I do that? Well, I need to go through the list again. So I need another loop. Okay, so inside of this loop, I'm solving a sub-problem that needs a loop. So there's nothing special about nested loop. You use a loop because you need a loop. Okay? So it's not some special concept that you're learning. You use a loop and your solution or sub-problem needs a loop to solve it. So for J in range, so the second loop is going through the list. Okay, the second loop is going through the list so I can compare to L of I. Okay, so I'm comparing, is L of I, the card I'm holding in my card description, is L of I equal to, now I'm going through all the elements of the list from beginning to the end to L of J. If they're equal, I can stop. I found duplicates and I can return true. Okay. And finally, when all of this is done, if I'm outside of the loop and I never found two that are the same, I should return false. There are no duplicates. Okay, there's a solution. Is it correct? Francois, is it correct? Francois.
No, because you would compare the same, you would compare the it would be always true.
Exactly. Actually, if somebody asks you, what does this program do? Correct answer would be, it always returns true. You have to, in our description of what you're doing in the card, what is hidden in my procedure is that I'm holding my card. So I never compare myself to myself. I say I take a card and compare it to everybody else. In the code, you have to make sure that you are not comparing a card to itself. Okay, so let's just, at the very beginning, we do it. Let's just see it. I is 0 here. So we are comparing L of 0. Okay, then we come to this loop. J is 0 first. And first time you enter the loop, you are comparing L of 0 and L of 0. Of course, if you're comparing L of 0 and L of 0, you're going to get true. You're comparing a card to itself. Okay, so you have to avoid here When are you done? When can you say that you find duplicates? First of all, the two elements are the same, and you need that they are not actually the same element. Okay, you need that the two elements have the same value, but that they are not same elements. So what should I put here, where my cursor is? Anybody can speak. What should I put here?
I not equal to j.
Exactly. When am I the same? When I'm comparing L of I and L of I, when I'm comparing two elements in the same position, right? So I want that the two elements in my list, I'm checking, are they the same? And if they're not the same actual element, so I is not equal to j, then I return true. Okay, so now our solution is correct. Jason, I'm going to get to questions once I do the analysis. All right, so let's analyze how many operations does this do. All right. So here, again, what does this do? First, every time we enter this loop, what is executed is something like I is equal to 0, I is equal to 1, I is equal to 2. That's one operation. How many times? So we have one operation, and every time we execute the loop. So how many times do we execute this loop? Again, the size of L is n. So what should I put here?
N.
2n.
N. So here, this loop is executed n times. Each time we do one operation. So this costs us n operations. Okay, we come now to this loop. Every time I execute this loop again, what is executed is something like j is equal to 0. Next time I go, j is equal to 1. So every time I execute it, I do one operation. But how many times do I execute this line?
N times.
N.
No,
N
squared.
N squared.
n squared. Okay, this line, so let's see why. It's important to understand why. This line is executed n squared times. Okay, so let's see why. Okay, so let's look at the outside loop here. When I enter this loop, first time I enter this loop, I is equal 0. When I is equal 0, so first time I enter the outside loop, I do this whole loop from the beginning to the end, from 0 to n minus 1. Okay, so when I is 0, I execute this line n times. Next time I enter this outside loop, I is going to be 1. So I is equal to 1. When I is equal to 1, again, I come to the beginning of this loop for the first time. Again, this loop is executed n times. So when I is 1, I execute this from 0 to the n minus 1. So I execute, again, I revisit the whole list. So I execute this inner loop n times again. Let me try to line these things up. Next time I enter this loop, I is equal to 2. And then this starts from the beginning. It goes from the beginning of the list to the end of the list. So this line, just for I is equal 1, is executed n times, and so on. Last time I entered the loop, I is equal n minus 1. So when I enter here, this again is executed from beginning to the end, so n times. So we have n plus n. Each time we enter the outside loop, we do this loop n times. How many times do we enter the outside loop? N times. So we do n plus n plus n, n times. So that's n squared. N plus n plus n. If I do that n times, I get n times n, which is n squared. Okay. So this line is executed n squared times. This costs us n squared operations. All right. What about this line here? Well, this line is executed as many times as this line here. Okay, so that's n squared. And each time I execute this line, I do one comparison, I do second comparison. You can see that each time you execute this line, you do 2 operations. And how many times you do that line is n squared. This is a return statement. Remember, each function terminates after return, so you do this once, okay? This one too, you do this once. So what is the total number of operations? We have n, then we have n squared, then 2n squared. So we have 3 times n squared, plus we have this one n here, plus n, plus we have 1 plus 1. But in fact, you either return true or you return false. You don't return. It cannot be that both of them you execute. So this is actually plus 1. Not that it matters, because we are now going to remove the constants. Okay, let's remove the constants. What are the not in the exponent? You're not going to do n squared and I'm now going to remove the exponent. No, don't remove the constants and exponent. Just the low down constants. So I remove a 3. I remove a 1. So I get that this is big O of n squared plus n. I remove all the constants. All right, but what you want really is just to keep the fastest growing term, the one that gives more operations. So for example, if our list has 1,000,000 elements, this is going to be 1,000,000, n is 1,000,000, but this is gazillion. I don't know, it's 1 followed by, was the 12 zeros. So this one dominates. That's why you keep just this fast growing thing. But if you want how officially to get rid of it, you can say this is at most, n is less than equal than n squared. So this is at most n squared plus n squared, right? Because n is less than n squared. This is 2 times n squared. Then I remove a constant and I end up with O of n squared. In other words, what you're really doing here, you just look at the functions, what's dependence of n, and you keep the highest dependence of n, and that is n squared. So this is O of n squared. This is quadratic algorithm, okay? So we found a solution for duplicates that is quadratic. Can we do better? Does anybody have a suggestion for better than quadratic algorithm for duplicates? Go ahead.
I think I have a solution.
Go ahead.
If we do one for loop, and for each item in the list, we remove the item from the list, then we put a line with if that item in the list.
Ah, very good. Thank you. So, okay, sorry. Yes. I know what you want to do.
Okay.
But that's also quadratic. When I was telling you, here's why, I can do analysis for you on the side of that solution. Maybe I'm going to add it into the notes so you can see the analysis. But your solution is correct, but it's still quadratic. When I was saying that you have to be careful when you are calling, and thank you for suggesting that, because it really reminded me of something important. I said when you make a function call to Python, you have to be very careful. You have to know how much it costs you. But here's another one that looks like a function, doesn't look like a function call, but it's very expensive one. It's in. If you're asking something like, is 10 in L? This looks like an innocent one. You're asking, is number 10 in list L? But this costs you O of n operations. In goes through the list, checks every single element, and checks, is it equal to 10? In is very expensive. Okay, so your solution is correct, but it would also end up being quadratic. Any other solutions?
I have an idea, but I'm
Yeah.
not positive if it would work or what the time complexity would be.
Yeah.
When you have the data structure of a set, it's
Oh, yes, you're right.
unordered and
Yes.
no duplicates. Could you just like create a copy, run through each one, and then compare the
So
lengths?
Yes. So what you sets are very powerful, but sets also rely on sophisticated math, and we haven't covered it yet. And it's not easy to understand why sets are fast. They really relied on probability and, in fact, even number theory. We're gonna study sets. I'm gonna tell you their speed, but we're not gonna do analysis of sets because it really requires more advanced things that you're gonna see in your second year. Okay. All right. So what was one of the tools? Let me give you a hint. What was one of the tools that we saw in a previous question, which was for the maximum, it wasn't helpful because it took more operations than the maximum that we developed. But now our solution takes quadratic number of operations. Okay. So let me ask you something. We were looking here for duplicates and assuming we know nothing about the data in L, and we didn't. What if I sort L? Remember, sorting costs you, I said, sorting of Python costs you n times log n. That is way smaller than quadratic. Well, not way. By the way, there are problems for which we only have exponential solutions. So quadratic is beautiful. I mean, it's a dream come true. N to the 100 is beautiful compared to exponential. Exponential is like 2 to the n. Okay, but here, what is this? This is n squared is n times n, right? So here we are comparing, the first term is the same. The second one, we are comparing n to the log n. Log n is exponentially smaller than n. Remember, log of 1,000,000 is 20, and here we would get 1,000,000. Okay, so we can afford to sort because it only costs us this much. If we sort duplicates version 2, if we first sort list L, and I'm going to show you experiments. I'm just going to run a code that I prepared for you. You will see dramatic difference, and I'll show you how dramatic. So we sort first. Okay. Now I know something about the data. Now I know my list is sorted from smallest to largest. So if I have two elements that are the same, where do they have to be? Do I know something about two elements that are the same? Anybody?
They have to be right beside each other.
Exactly. So now I don't have to compare every pair like what we were doing here. It's enough that I go through the list once and I just compare two elements next to each other. I compare consecutive pair. It's enough that I go through the list once and compare 1 to the 2, 2 to the 3, 3 to the 4, 4 to the 5, and last two elements until we get to the last two elements. If I go through the list like that and compare only consecutive pairs, if I find two that are the same, fine, we are done. If I don't find two that are the same, I can safely say there are no duplicates. Because if there are duplicates, they have to be next to each other somewhere. Okay, so let's code that. We are just going through the list once. And I'm talking about compare this element to the next one. So I better know the position, right? For I in range len of L, I'm comparing element L of I. Is L of I same to the one that come after? So L of I plus 1. Okay, so I'm comparing L of I plus L of I plus 1. Okay. If they are the same, I return true. Otherwise, if I go through all the pairs, return, and never find two that are the same, I can safely return false. By the way, here you have to be careful. You don't want to go to the end of the list, because if L of I is the last element of the list, L of I is the last element of the list, then you are trying to compare it to L of I plus 1, so you're outside of the list. So you have to go to the, you don't go to the last element, you go to the second of last element. That's when you should stop. Okay, that's the last time you can compare L of I to somebody after. That's our solution. Let's analyze it. So this we already determined costs us n log n. This line, we are just again assigning every time we executed I is 0, I is 1, it's one operation. How many times do we do it? We do it at most n. In fact, we do it n minus 1 because we go from first element to the second to last element. This is just comparison of two numbers. It's one operation times the number of how many times we execute that line. Again, it's at most n minus 1. So we do this n minus 1 times one operation. This is 1 and this is 1. Okay, so what's the total number of operations? We have n log n plus 2n, we have here 2n minus 2 plus 1, so that is minus 1, okay? So we remove the constants, we get n times log n plus n. But then this one is faster growing than this one, right? So this is n is less than n times log n. So you can just write this. This is at most 2. This is at most n times log n. Plus n is less than n times log n. So that is equal to 2 times n times log n. We remove a constant and we get big O of n times log n. So this solution, or rather you really can eyeball it, this one. You look at dependence of n, this term is n log n, this term is n, so really the biggest one is this. So that's what big O notation does. So big O just says, I'm keeping the fastest growing term in n and removing everything else, okay? That's what O means, that's what I did. This is n log n, roughly number of operations. So we have a better solution. So now let me show you the experiments. How much better? I'm just going to run them. You're going to see this end of the class. I prepared them already. So here are the experiments. So here's what it does. The code. Let me explain it. This thing here creates the list of 10 million elements. So this size of the list, this is called list comprehension. You can learn it by yourself. It's fun, actually, nice thing in Python. It creates a list of integers without duplicates. And then it shuffles them. All right. And then we call first our function that we did with sort. It's over here. I'll share this code with you so you can run this at home. So we first we want to know, are there duplicates in this list X? Okay. And we print the answer. So you should print true or false. Okay. Then we shuffle it again, and then we call the other one, the n squared one. So this is on a list with 10 million elements. Okay, so let's run it. Okay, so first the one with the sort is working. And while I'm speaking, in about 10 seconds or something, it should show the result. All right. Let me tell you, and you can run this at home and leave it to see when the other result is going to show up, the quadratic one. But in the meantime, let's do some little bit of math. So we have, so it's already done. The one with the sort, n log n1 is already done. Now the quadratic one is running on exactly the same problem, solving exactly the same problem on the same list. Okay, so the quadratic one is, let's see how many operations it does. It has 10 million elements. So 10 million, that's 1, and then 1, 2, 3, 1, 2, 3, this many zeros squared. So it does this many operations at least. So it does n squared operations. Okay, so let's say you have a really good computer that can do 1,000,000 operations per second. Okay, so let's see. So I divide this by 1,000,000. I'm going to use integer division. Divide by 1,000,000 because these are divisible. I divide this by 1,000,000. 1, 2, 3, 1, 2, 3. I get how many seconds we're going to wait, right? If it can do 1,000,000 operations a second, and I have to do this, and I have to do this many operations, this gives me how many seconds I'm going to wait for the second false to appear. Okay, to us humans, this number of seconds, this doesn't tell me anything. Let me convert to minutes. Okay, this is how many minutes you're gonna wait. Okay, actually I don't need to do any more the integer division. Okay, so this is how many seconds you're going to wait. Okay, so sorry, that's how many minutes you're gonna wait. Okay, but okay, let me check it hours. I divide by 60 another time. Oh, it's 27,000 hours. Okay, I still don't have a good notion of how long is that. Let me convert it into days. Okay, I divided by 24 to get how many days. Oh, it's 1,157 days. Okay, let me divide it by 365. You're gonna wait for more than 3 years for the second false to appear here. That's how different quadratic is from n log n. This is why it's so dramatically important. This is what makes a valuable programmer. This is what makes somebody who every company is going to hire if you can understand and be good in efficiency of algorithms. So And you may say, okay, you're exaggerating. When are you going to be working with 10,000 numbers or something? First of all, we are living now in a world of big data. You're going to be working with it all the time. But even before that, just think of an image, single image that you take with your phone. It has 10 million pixels, right? So if what you're coding is, let's say you want to change something, you want to manipulate your pixels to design another in a graphics game, to manipulate it such that you get a different image. Just manipulation of that one image, if you're not careful, you'll end up with doing quadratic number operations, and somebody's going to wait for your game to display that image for 3 years. Okay, so graphics is, that's why actually those of you who are playing games, you need a super fast machine with very efficient algorithms, because you're actually manipulating images. But this for the video games and so on. But just to convince you, this is why you at studying computer science, this is what it's about: efficient algorithms, correct algorithms, and figuring out when you actually have optimal solutions for the problems you're trying to solve. Okay, so that's it for today's lecture.